In this laboratory lesson, we're going to develop the Python node that receives a velocity message in the robot's reference frame, convert it to a velocity command for each of the wheels of the robot, and publish each of these velocity in the corresponding topic that actuate the corresponding wheel of the robot. If you're only interested in the C++ development, then you can skip this lesson and go to the next one, in which we will develop the same node with the same functionalities in C++. Let's insert this new node inside the BumperBot controller package, so this one here, and let's start by creating a new subfolder called as the package itself, so BumperBot controller. In fact, as we used CMake as a build type for the BumperBot controller package, the BumperBot controller folder was not automatically created, and so we had to create it manually. And also within it, we need to create a new script called init.py that we can leave as it is, so that we can leave empty, and then we can create the actual node. So let's create another file and let's call it simple controller.py. Here, let's start this script by indicating the directory of the Python interpreter. And so this is in the folder user bin, and we are using Python 3. We need to include this instruction here, so we need to specify the directory of the Python interpreter as the build type that we have chosen, so the CMake is not able to automatically detect it. Let's also import the RCL.py library, from which, as always, we can use all the ROS2 functionalities, and then still from this library, from the node module, let's import the node class. And now we can use this class to create a new ROS2 node. So let's create a Python class called simple controller, and this class inherits from the node class, which is defined in the RCL.py library, so it implements a ROS2 node. Let's start this class by defining its constructor, so the function that gets called whenever we create a new instance of the simple controller. So this is the init function, init, okay. And whenever we create a new instance of the simple controller class, as a first thing, let's initialize the base class part, so the node part. We can do so by calling the constructor of the base class, so the init function of the base class, which takes a string as input, and this is the name that we want to provide to the node, and let's call it simple controller. Now everything is correctly initialized, and you can move on to declare two parameters of the node. As you may recall from the simple parameter laboratory lesson, to declare a parameter of a Python node, we use the function declare parameter, which we have inherited from the node class. So let's use it twice in order to declare two parameters of this node. And let's call the first one wheel radius, and the second one wheel separation. These two variables, these two parameters, are crucial for the implementation of the differential kinematic equation, and I decided to include them as node parameters so that, for example, you can reuse this same class, so the simple controller class, also for another differential drive robot, also for a differential drive robot with a different wheels, so with a different wheel radius, and also with a different distance among the wheels, so with a different base. Anyway, by default, I set the values of these parameters to the parameter of our robot, so of the BumperBot. And so the wheel radius is 0.033 and the wheel separation is 0.17. Then, after declaring a node parameter, we also need to read it, so to read its runtime value, the one that is assigned at the startup of the node. To do so, we can use another function that we are inheriting from the node class, and this is the get parameter function. So let's use the get parameter function, and let's read the wheel radius, and so let's read the get parameter value, so let's take its value, and then let's take it as a double, so double value, as this is a decimal number, and let's store this value here, so the one that we have read from the wheel radius parameter, within a new variable, and so let's call this one wheel radius, and so let's store within this variable here, wheel radius, the output of all of this function here, so basically the value of the wheel radius parameter. We can copy this same instruction and we can paste it below. Let's change the name of the variable into wheel separation, and also the parameter that we want to read is the wheel separation parameter. Now, before starting all the functionalities of this node, let's print these two values that we have just read. So let's print these two parameters in the terminal with the get logger function. So let's print an informative message, and this message says using wheel radius, and then let's print a decimal number, which is exactly the wheel radius variable. And also let's do the same, so we can copy this line, and let's also print the wheel separation, and so this is in the wheel separation variable. And then let's create a publisher object that we're going to use to publish velocity commands to the wheels of the robot. So let's do it with the create publisher function, and let's store the result of this function in a new variable called wheel command publisher. So let's call the create publisher function. As we saw in one of the previous laboratory lessons, when we moved the robot in Gazebo through the ROS2 control command line interface, to actuate the wheels, we need to publish a message in the simple velocity controller commands topic. So let's declare that we want to publish in the simple velocity controller commands. And as we saw in that lesson, in this topic there are accepted float 64 multi-array messages. So let's import this type of message from the standard messages library. So from the messages, let's import the float 64 multi-array message, and let's use this one here within the create publisher function. So this is the first argument. And then we also need to set here the queue size, and we set it to 10. With this publisher now, we are able to send velocity commands to the wheels. So now let's also create the subscriber to the velocity commands that are coming from the joystick. So let's create a new subscriber object, and let's call this one velocity subscriber, and we can initialize it with the function create subscription. So this function here takes as input the name of the topic in which the joystick is going to publish the velocities, and this is the bumperbot controller command velocity topic. And then we also need to indicate the type of the message that is published in this topic, so that the joystick is publishing in the bumperbot controller command velocity topic. And this is a twist stamped message defined in the geometry messages package. So let's import it from the geometry messages. From the messages, let's import the twist stamped message, and so let's declare that this subscriber here is going to receive twist stamped messages within this topic here. Then we need also to specify the name of the function that has to be executed whenever a new twist stamped message is published on the bumperbot controller command velocity topic. So here, as a third parameter, let's call this function velocity callback. And also in this case, so also for this subscriber, let's set the queue size to 10. Now we need to define this function here, so the velocity callback function, and we can define this function here still as a member. So let's pass the self. So this is still a member of the simple controller class, and as this is a callback function, it receives as input the message. So the message that was just received within this topic here. Anyway, before implementing the logic of this function, let's first complete the constructor of the simple controller class. And let's do it by defining the matrix that we are going to use to convert the velocities from the robot's reference frame to the rotation of the wheels. And so let's create a new variable that will do this. And let's call this one speed conversion. And to implement a matrix in Python and also to perform some operation with matrices, there is a very useful library available in Python called NumPy. So let's import this library. Let's import NumPy and let's give it a name np. And now we can use this library here in order to initialize our speed conversion array. So basically a matrix is nothing more than a multi-dimensional array. So let's create an array, a NumPy array, and the first element of this matrix is given by the radius of the wheels divided by 2. So let's create a matrix, and the first element is the variable wheel radius divided by 2, and then the second element of this matrix is again the wheel radius divided by 2. Then with this we have completed the first row. Then let's also define the second row, and the first element of the second row is given by the wheel radius divided by the wheel separation. And then we have the fourth and last element of this matrix that is given by minus still the wheel radius divided by the wheel separation. Let's format it better. So here, so now we have that this is the first row of our matrix and this is the second row of our matrix. With this we have stored in this variable here, so in the speed conversion variable, the matrix that implements the differential kinematics equation for the conversion of the velocity. So before actually using this matrix here, let's display it in the terminal. So again, with the get logger function, and then let's display an informative message that says the conversion matrix is, and then let's print the matrix itself. And so let's print the speed conversion variable. Now the constructor is completed, so the simple controller constructor is completed, and now we can move on implementing the velocity callback function that is called whenever a new velocity message is published on the BumperBot controller command velocity topic. The message type that is published in this topic is twist stamped, and if we take a look at its definition in the geometry messages library, apart from some metadata, it contains a command for the linear velocity and another one for the angular velocity. So here, within the velocity callback function, let's create a new NumPy array, and let's call this one robot speed, and so this is a NumPy array, and let's create it from the message. So let's create a matrix, and the first element at the first row of this matrix is the message. Then let's access to the twist message, then to the linear velocity and to the variable x, and this represents the linear velocity of the robot along the x-axis. And now the second element, so actually the first element at the second row, is instead the angular velocity of the robot. So still from the message and from the twist let's access to the angular velocity and to the component along the z-axis. And now with this, we have extracted from the twist stamped message that we received the linear velocity v and the angular velocity w, and also we know which is the matrix ms for the conversion of the velocity. So now we can use all of this information to calculate the commands that we have to send to the wheels. Let's store these commands within a new variable called wheel speed, and we obtain the command for the velocity of the wheels by multiplying the inverse of the matrix ms by the vector with the robot's velocity. So first we need to calculate the inverse of a matrix, and with the NumPy library we can use the linear algebra module to calculate the inverse, and let's calculate the inverse of the self-speed conversion matrix that we have created, and now we need to multiply this one for this other matrix here, this vector here. And in order to multiply with the NumPy library, we can use the matMultiply in order to multiply matrices. And so let's multiply the inverse of the speed conversion for the robot speed. Now also this variable, so the wheel speed, is a NumPy array with just two elements that are exactly the velocity commands that we can now send to the wheels of the robot. So now we can create the actual message that we can send to the wheels of the robot so that we can publish within this topic here, so within the simple velocity controller commands topic. And so let's create a new variable called wheel speed message, and this is an instance of the float64 multi-array message. This message, so the wheel speed message, contains a variable data, and so here we can actually insert the vector. So we can insert a vector which contains a velocity for each of the wheels of the robot. The first element of this vector represents the velocity that we want to assign to the left wheel of the robot, and so let's access to the wheel speed NumPy array and to the element at the position 1, 0. And then also the second element that we can add to this message, here it should be speed message. Okay, so the second element is instead the velocity of the right wheel of the robot, and this is contained in our NumPy array, so the wheel speed, and is the velocity at the position 0, so wheel speed 0, 0. Now we finally have also our float64 multi-array message, so this one here, with the velocity command for each of the robot's wheels. And now we can use the publisher object to publish this message and request the ROS2 control library to move the wheels accordingly. So we can use the wheel command publisher, and let's call the function publish in order to publish the wheel speed message. With this we have finished, and so now we have published a message to the wheels in order to move them accordingly, and so now we can move on and define the main function. And here let's simply execute the function main. So let's define the function main, and as a first thing, as always, let's initialize the ROS2 interface with RCLPy init, and then let's also create a new instance of the simple controller class, and then in order to keep all these functionalities up and running, and so in order to keep the publisher and the subscribers up and running, let's use the function spin, so in order to keep the simple controller up and running. And then if we stop the execution of the node, let's destroy it. So let's destroy node, and also let's shut down the ROS2 interface with the shutdown function. With this, the simple controller.py script is completed, and now we can move on to installing it within the file cmakelist.txt. If you only followed the Python laboratory lessons, then most probably this is the first time you encounter this type of file. This is like an instruction sheet that is commonly used by the build type cmake to build and compile C++ node, but that we can also reuse to compile Python nodes. To do so, we first need to add the dependency from the cmake Python. So cmake Python, which is a build type that allows us to build and compile Python nodes. Then we can also add the dependency from the RCL.py library, which we have used in our script, and also here we have used the standard messages and the geometry messages. So let's add both of these dependencies, standard messages and also a geometry messages. Then after the find package instruction, we also need to use the function Python install package to declare that the BumperBot controller also contains some Python node that we want to compile. So here we need to insert the name of the package, and it is also possible to use the variable project name, which contains exactly this name here, so the name of the package. And finally, here, now that everything is set, we can install our Python node with the install instruction. So we want to install a new program, so with programs, and now we need to indicate where is located our Python script within our package. So it is in the BumperBot controller subfolder. Again, we can use the project name variable, and so this basically will contain the BumperBot controller, and then it is called simple controller.py. So this is our script, and we want to install it. So here we need to indicate the destination, and this is the lib folder, and within the lib folder we want to install it in the subfolder that has the same name as the package. So again, BumperBot controller, and again we can use this variable here, so the project name variable. We can save this file, and as we have declared here some new dependencies, we also need to add them to the package.xml. So actually here we need to add some dependencies. Let's add the dependency from the RCL.py library. Then let's add also another dependency from the standard messages, and also let's add a dependency from the geometry messages, and of course we need also to add a dependency from the build tool cmake Python. So we need a new build tool dependency. We can copy this one and we can paste it, and we need a dependency from the cmake Python. That's all we need. So let's save this script, and let's just conclude this lesson by building our workspace in order to see that actually everything is working. So if we open a new terminal and we go to the workspace, let's use the command build to build it and also to compile the new node. In the next laboratory lesson, after creating the simple controller for C++, we are going to launch it and to see how it works.